Welcome to the Explainer. Every single day, you double-click an icon and a program just appears. It's something we don't even think about. But that simple action, it kicks off this incredible high-speed journey deep inside your computer. So today, we're going to follow that journey from the click all the way down to the running code, and we're going to reveal the hidden mechanics of how a Windows process is actually born.
It really does feel like magic, doesn't it? 1 second you've got a static icon, and the next, a fully functioning application is right there on your screen. But in that split second, your operating system is performing this dizzying ballet of operations. It's a super, precise, engineered sequence that literally builds a new reality for that program, completely from scratch.
So here's our game plan. We're going to start with the mystery of that double click. Then we'll get into how every single process has two faces, one for the OS and one for itself. After that, we'll watch the kernel forge the process on its assembly line, and then see the loader add all the final touches. And finally, we'll tie it all together and see why this all matters so much for your system's security and stability. Okay, so that double click. It feels like such a simple command, but what it really is a request. And it's a request that has to travel from our world, the world of applications, across this heavily guarded border and right into the very core of the operating system itself. This might be the most important concept in any modern OS. This separation between user mode, where all your apps live, and kernel mode, which is the protected core where the OS does its thing. Just think of it like a fortress wall, and it's enforced by the CPU itself. It is the one thing that stops one misbehaving app from crashing your entire system. And check this out. This diagram from the Windows internals book shows us exactly how we get across that wall. See, a user mode request, something like create process, it doesn't just talk directly to the kernel. No way. It triggers a chain reaction, getting passed down through system libraries until it hits the final gateway, NT create user process. And that function is the key that unlocks the door to kernel mode.
Right, so now we're inside the kernel. The OS needs a way to manage this brand new process. And to do that, it creates two totally distinct but related identities for it. It turns out, a process has two faces, a private one for the kernel and a more public one for itself.
The analogy here is actually pretty simple. The eProcess structure, that's the kernel's confidential HR file in the process. It's got all the sensitive data the OS needs to manage it. But then there's the process environment block, or PEB. That's more like the process's own ID badge. It's stored in the process's own memory, and it contains all the public info it needs to function. So let's peek inside that confidential file, the eProcess block. This thing holds the crown jewels. We're talking the process ID, its security token, which defines everything it can and can't access, its physical memory usage, and a list of all its threads. This is super privileged information, and for security reasons, it's completely firewalled off from user mode. Now, the PEB, on the other hand, is the process's public-facing toolkit. It's there to answer all the practical questions the process has, like, hey, where am I loaded in memory? What command line arguments was I given? Which shared libraries or DLLs do I have access to? The kernel basically builds this toolkit and then just hands it over for the process to use.
Okay, so all the paperwork has been filed. Now the kernel's assembly line really kicks into gear. It has complete control, and it starts to forge this new process, following a very, very specific blueprint.
And that whole assembly line is managed by one master function, NT create user process. This is the big one. It's the system call that takes that abstract request from user mode and turns it into a real, concrete construction project inside the kernel. And the kernel follows this blueprint exactly, every single time. Step 1, create the eProcess object. This gives the process its core identity. Step 2, allocate a private virtual address space, its own little sandbox to play in so it doesn't mess with anyone else. Step 3, initialize the PEB, its user-facing toolkit. Step 4, create the very first thread, the actual worker that will execute code. And finally, Step 5, create a process handle, which is basically a ticket that the parent process can use to manage its new child. And this brings us to a really key distinction. After all those steps, we have a process object, but as the book Windows Internals puts it, the Windows Executive Process object is completely set up. It still has no thread, however. And what that means is we have this perfect, fully formed container, but it's empty and it's inert. It needs a thread, an actual agent of execution, to bring it to life. So, the kernel's heavy lifting is now done. We've got a process and we've got a thread ready to go. But it's still not running our application. For the final stage, control gets passed back across that boundary, into user mode.
So here's a common misconception. The very first code that runs in a new process isn't your app's code at all. It's a system's image loader, which is the special routine tucked away inside the core NTDLL library. This loader's job is to prepare the stage before your program can even think about starting. You can think of the loader like a meticulous stage manager. First, it sets up the heap, which is where dynamic memory allocations are going to come from. Then, it reads the application's manifest to find all the other DLLs it depends on, and it loads them all into memory. After that, it has to resolve all the function calls between them, kind of like connecting all the wires. And only after this entire checklist is complete does it finally hand over control to your application starting address. And here's the proof. This process monitor trace captures that exact moment. Take a look. As soon as notepad.exe is created, what are the very next things that happen? Load image. The loader is immediately pulling in its essential toolkits, ntdll.dll and kernel32.dll, before a single line of Notepad's own code ever gets to run. So, that's the journey. From a simple click to a fully running process, it's this complex dance across system boundaries, and it all happens in a flash. Which, of course, raises the big question. Why? Why all this complexity? Why is this intricate process so fundamental to how your OS actually works?
Well, the payoff is just immense. That user and kernel mode separation, that's the bedrock of system security. It's what stops a buggy application from scribbling all over critical OS data. The private address space for each process, that gives you stability. When one app crashes, it doesn't take everything else down with it. And the whole system of shared DLLs is just incredibly efficient. Core components like NTDLL are loaded into physical memory just once and then shared among all the running processes, which saves a huge amount of RAM. So the next time you launch an app, just take a second to appreciate the hidden ballet that you just commanded. The birth of a process is an absolute marvel of engineering, and it's all happening invisibly in the blink of an eye. It really makes you wonder, doesn't it? What other digital ballets are hiding in plain sight, just behind our simplest clicks?
Help me out, please smash that like button, leave a random comment and subscribe if you want to become a better hacker.